All right, so we are in 6.3, starts on page 137 of the textbook. Okay, so we've seen multiple methods of proof so far. We've seen direct proofs and indirect proofs, which is contrapositive and contradiction. For some reason, I wanted to say Contra Costa, but that's the county we're in. So that's unfortunately Contra Costa is not a style of proof. But another style of proof is called induction. And so this is akin to, let's say we are trying to climb a ladder. So maybe we're trying to get up somewhere high. And the process with induction is like when you're climbing a ladder, you have to take the first step and then the second step and then the third step and so on. So like we have to climb the rungs of the ladder one at a time. And so induction is all about, let's do the first few and then assume that it works somewhere in the middle. And then if we can prove that for some general case in the middle, we can go from one to the other, then all the other rungs in the ladder exist, right? This is inductive reasoning. So we start with what we call a base case. And then we have the inductive hypothesis. And then if we make this arrow purple, then we've got the inductive step. So the whole idea is to say, I don't want to write down all these steps of the ladder. Like, I don't want to be like, I'm going to take the 230th ladder rung and then the 231st ladder rung. I don't want to do that. That's time consuming. It's tedious for everyone involved. So let's just shorten that into this process that we call induction. So we start with the base case. And if you're familiar with recursion, it's sort of similar, where with recursion, we have a base case, which is the simplest possible way we can return a value for this function. And then we have the recursive case, which handles everything else. And so induction is super similar, where we start with the base case, and then we assume we're somewhere in the middle, and then we prove the very next step. And then once we do that, then we can be, okay, all the other rungs of the ladder exist. This is especially useful. So if you took my 222 class, we showed this for, what was it? Like, now I'm blanking. We show this for like Fibonacci of and factorial, where we assume that it works up to a certain point, and then we've got the very next point. So yeah, so the book has what it calls principle 6.3, where this is the principle of mathematical induction, which says we have some formula or predicate n. And so if you're familiar with like f of x is equal to some equation, this is the same sort of thing, where p is basically just a function. And so we've got some function p of n, where we take n as input, and then we have some output as a result. And this is super common with induction, where we will have induction is used really often to prove like a sequence of things, where if you've got like a summation or repeated multiplication, or it's also used in like graph theory, where you're like building up a graph that looks like such and such, where you're building something up you don't want to have to enumerate every possible. So you prove the first few, then you prove a general case in the middle, and then that gives you the property that you're trying to prove. And so we have some, the book calls it a predicate P of n, and then so let P of n be defined for all, and then typically when we're proving induction, it'll give you some range of numbers that we want to define this for. So for this case, it's all the natural numbers. Sometimes you'll find it all integers, basically something that we can count on. And so let P of n be defined for all natural numbers, and then we suppose that the following statements are true. And so 1 is we prove that P of 1 is true. This may vary depending on the kind of statement that we're proving. Maybe we need to prove P of 0. So this is essentially the base case. The second step is that we say for all k greater than or equal to 1, if P of k is true, then P of k plus 1 is true.
You go back to the star P of 0 to explain why.
So P of 1 is being true. This is so this works for, like, if we're trying to prove something over the natural numbers, we want to prove that the base case is true. So the natural numbers start at 1. If we're proving something for integers or something where 0 is allowed, then we would need to start at 0 instead. So it depends on what set of numbers we're trying to prove this statement is true for. And so I'll add sometimes P of 0. So you may not always start at 1. All right, so step 2, this is called the inductive step. And I'll say if P of k is true, here, maybe let's so this is, no, don't do this loud. Where's that color? Okay, good enough. Okay, so the pink underlined part, when we assume that P of k is true, that's our inductive hypothesis. So remember, like, when we're proving something, we assume something is true at the beginning. That's our hypothesis. And then we follow it from there. And once we've got that, then we can say, once we do these two things, then P of n is true for all natural numbers. So if we're able to prove the base case and we're able to prove the inductive step, then we've built our whole ladder. So it ends up being, so we prove the base case, and then we prove we do the induction hypothesis, and we prove the inductive step, and then we can assume that now the rest of our ladder exists for any number that we're going to give it. All right, let's look at an example. So this is example 69 on page 138 of the textbook. And so we want to prove for any number n in the natural numbers that the sum of squares, so 1 squared plus 2 squared plus so on and so forth, plus n squared, we want to prove that it's equal to n times n plus 1 times 2n plus 1 over 6. This is what we're trying to prove. First step is to determine what's the actual predicate that we're trying to do. So what's the function that we are trying to prove? And that's basically just the thing that I wrote. So in this case, it's easy.
The entire thing?
Yeah, so P of n is the equation 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared up until n squared. So where n is our input. And we want to prove that this is equal to this handy dandy formula, where n times n plus 1 times 2n plus 1, all divided by 6. That's where we want to get to. So to prove it, first we identify the base case. And since we're proving for all natural numbers, zero's not included here. So we show for P of 1. So P of 1 is on the left-hand side, the sum of things up to 1 squared. So the left-hand side is just 1 squared, which is equal to 1. Very boring. We like that. The right-hand side is 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. And this is 1 times 2 times 2 plus 1 is 3. 1 times 2 times 3 is 6 over 6, which is 1. So notice that I didn't, I'm tackling both sides of the equal sign separately because I can't assume what I'm trying to prove. And so we get that the left-hand side equals 1, the right-hand side equals 1, 1 equals 1. So we've proved the base case. So left-hand side is equal to the right-hand side. Check mark. Now, we'll do the inductive hypothesis. Which is we're going to assume the statement is true for P of K. So we're going to choose some number later on down the ladder for which this is true. We'll call that number K. We show PK plus 1 is true. And so we assume that P of K, which is 1 squared plus 2 squared plus so on and so forth plus K squared. We assume, so we can write the equal sign, that this is equal to K times K plus 1 times 2K plus 1 all over 6. And so now we want to show that it's true for P of K plus 1. So we can, just for our benefit, we can say we will show P of K plus 1, which is 1 squared plus 2 squared plus K squared plus K plus 1 squared is going to be equal to, but I'll write a question mark over it for now. And then for each of these ends, we just substitute in a K plus 1. Right? So if this is in terms of n, and we want to find P of K plus 1, we just put K plus 1 in for n. So this is K plus 1 times K plus 1 plus 1 times 2 times K plus 1 plus 1 all over 6. So we want to show that those are equal. So we'll start with P of K. So this technique for induction is you start with the equation in terms of K, and you're like, okay, I want to get to a K plus 1 on both sides. And so we do that. So we've got an equation here. So we say adding K plus 1 to both sides of P of K, we get 1 squared plus 2 squared plus K squared plus K plus 1 squared. And then we write our big, long, fancy equation, K times K plus 1 times 2K plus 1 over 6. And we add K plus 1 squared. All right. So once we do that, then typically the strategy is now you ignore the left-hand side and work to simplify the right-hand side into something that looks like this. So let's look at the right-hand side. We can multiply a term by 1. And so let's multiply it by like by 6 over 6 to get it onto the same fraction. And so we have this is equal to K times K plus 1 times 2K plus 1 plus 6 times K plus 1 squared all over 6. All right, so now they're on the same fraction, and both of these terms have a K plus 1 in them, so let's factor that out. So we've got K plus 1 times K times 2K plus 1 plus 6 K plus 1. And we're still all over 6. And we can FOIL this out. So we've still got k plus 1 out here. And so this is going to give us as an intermediate step 2k squared plus k. And then this is 6k plus 6. And so adding those two binomials together, or yeah, so we get 2k squared plus 7k plus 6. Still all over 6. And now we're almost there. So this is something that we can factor now. So we've combined it all together, and now we can factor it. But factor it in a way that it looks different from what we had before. So this gives us, say that again. And so this gives us k plus 2 in the interest of time, and then 2k plus 3. So now that we've factored this out, we don't really need the square brackets anymore because it's all multiplication over 6. K plus 1 times k plus 2 times 2k plus 3. We scroll back up. K plus 1 times k plus 2 times 2k plus 2 plus 1, 2k plus 3. We've gotten to a form that looks like the thing that we're trying to prove. And so that's k plus 1. Let's add some words. Which is p of k plus 1. Therefore, by the principle of mathematical induction, I'm running out of room. P of k plus 1 holds. So P of n holds for all natural numbers. And there, we did it. So now we've proved this statement by induction. And so now we can say that our P of n formula, like that's always going to hold for any natural number that we throw at it. And the key to having, so it seems kind of like cheating where we're like, let's prove the first one and then choose something in the middle. And then, oh, look, it's true forever. But the key is, especially like you'll see this in proofs all the time in this class, the key is the generality. So it's not that we're choosing like a specific example somewhere in the middle, it's that we're choosing a general example somewhere in the middle. So we're choosing K instead of 2,000 or 50,000. We're choosing some number K. It could be anywhere as long as it's not like just one, which we've already proved. So if we choose a general number somewhere in the middle and then prove that this sequence holds, then we're good. Questions so far? Induction is tricky. Okay. Let's look at primes, and then if we've got time, we will do the problem. I changed the schedule. This is what, 6.3. So 6.3 used to be number 2. The problem for this section But I don't like number 2, so I made it number 3, which is easier. So if we've got time at the end, we'll do that. But let's move on to primes. This is section 7.1 in the book. It's part of chapter 7, which is on number theory. Are any of you also in number theory this semester? No? Okay. Wait, I think number theory is off for this semester. Maybe. Anyway, if you're interested in this, the department offers a math class that's number theory, which is more of this kind of thing. So basically, how can we solve these puzzles with numbers? Okay, so primes are great and mysterious, but we have a definition for them, where if we've got some number a equals b times q, and we find that if q is equal to plus or minus 1 or plus or minus p only, so those are the only possibilities for q, then the number is prime. If there's any other divisors, then we say A is composite. All right, so that's a prime number. And we know this from earlier as well. So something that you may not have heard about. So this is theorem 7.1, which is the prime factorization theorem. Factorization theorem, which says that every integer greater than or equal to 2, so we kind of disregard 1. And then every integer is either prime or is a product of primes. And so we can write for, if we call that integer n, we did call that integer n. So we can say that n is equal to, so this is our equation with lots of letters, but essentially, like, we take the first prime and it's a product of powers of primes, and so we can multiply that by some exponent and the second prime by the second exponent and so on, which is a lot of letters to basically say we decompose the number into its prime factors and multiply them all together. So for example, the number 48 is 2 times, no, that's correct, incorrect. That 2 to the 4th times 3 to the 1st. 90 is equal to 2 times 3 times 3 times 5. So we can write a number in terms of its prime factors. And this is 2 times 3 squared times 5. And so in terms of the equation with all of the letters, this 2 is P1, exponent 1 is just 1, because 2 to the 1 is 2. Prime number 2 is 3. The exponent number 2 is 2, because we raised 3 to the second power. Prime number 3 is 5. Exponent 3 is, again, just 1, right? So the idea is we write a number as a product of primes. And the other thing this theorem says is If you write it in a way, write such that P1 is less than P2 is less than PK. So you write it in the primes in ascending order. And so we've got 2 first, then 3, then 5. And then this representation is unique. So there's only one way to write a number as a product of ascending primes. Okay, so we can write stuff as a product of primes. And so the first question is, how do we determine whether a number is prime? So that's our first question. And we've got a theorem for that, which is, again, so we're going to let n be greater than or equal to 2 because 1's wonky. So n is greater than or equal to 2. And the theorem says if no prime number, let's call that prime number p, and let's say we'll limit it to being up to the square root of n. So if no prime number p with that restriction divides n, then we can say n is prime. So let's think of small examples. So let's say, let's consider 10. So square root of 10 is about 3. So it's slightly greater than 3. And so now we can check the prime numbers up to 3, which is just, so 2 divides 10. And once we get there, then we say 10's not prime. Let's take 11. The square root of 11 is a little bit also more than 3, which makes sense because they're right next to each other. And so we ask, does 2 divide 11? No, because it's not even. So I'll write the little slash through the bar there. Does 3 divide 11? Nope. And then we've reached the square root of 11. And so since no prime number is up to that point, divide 11, then we can say 11 is prime. Yeah.
Is there a way to do it faster if you were to do a higher number, like without going through each individual step, or is it like intentionally a lengthy process? Or is it just like built in? Sorry.
Yeah, so there's multiple ways. So this is one way to tell if a number is prime. Here. All right, so there's the trial division. That's what we just talked about. Simple methods. Da, da, da. There's the sieve of Aristophanes. Which is like a recursively a way to mark things as composite. And so once you do that, then you kind of get the numbers which are prime after that. Like there's other ways to do this as well. Fermat primality test, Fibonacci test. You could win $620 if you can disprove this equation, probabilistic tests, and so on. So this is just one, like, because you're right, this is not great, but it works. All right, so that's a way to choose that to find that it is prime or that it isn't prime. The homework question of So the homework question for this is number 1 in this section, which is like, is 127 prime, which you go through this process, is 667 prime, is 1987 prime. And then it gets tricky where it's like, is 2 to the 50 minus 3 to the 20 prime? And I don't want to write all that out. And so here's where you have to like use number tricks and algebra to get where you want. So this is where you also have to remember like the exponent rules, where if you have x to the, like let's say 2a, right, no, yes. So the hint I'm going to give you for this is x to the 2a. So if a is 25, we can write this also as x to the a squared. And so 20 is also a number divisible by 2. And so if we've got y to the 2b, this is equal to y to the b squared. And I guarantee you there is a formula of, what if we've got x squared minus y squared? How can we write that as the product of two things? We can do it. And other stuff like that. So yeah, so we got to get into like the little number tricks. So for this homework, I encourage you talk with your neighbors, maybe set up a study group time and work through it together. You could go to the STEM center, even though there's not a tutor for this class, but you could go there and work on it together. Collaboration. Okay, so that's my hint for the homework. And the second big question that we want to prove is, so we've got primes. We can tell if a number is prime. The next big question is, well, how many of them are there? So how many primes are there? And this is the second of the, if I see you in 10 years walking down the street, I would like you to be able to prove this. For some reason, the square root of 2 one always sticks in my head, but the prime numbers one, I always have to refresh. So, so far I'm not doing great on the 10 years, but learning's a continual process. All right. First of all, talk to your neighbor and say, how many primes do you think there are? Right, yeah, there is an infinite number of natural numbers. So I think it would intuitively make sense there's infinitely many prime numbers. But how do we know? How can we prove that? if there was actually like, let's say like 140,000 primes, this would like break cryptography, um, which would be like a big problem. So there being infinitely many primes is actually a really good thing. Okay, so this is theorem 7.4 in the book, which says there are infinitely many primes. All right, we're going to prove this by contradiction. So suppose not. And so the opposite of this statement are that if there's not infinitely many primes, then there's got to be finitely many primes. So there's not infinite, there's 140,000 or however many. So there are finitely many primes. The good thing with there being a finite number of primes is that we can find them all and we can list them all. So we can order them like P1 is equal to 2, and we can order that being less than P2 is equal to 3, and so on. So we can list all of the primes. We can compute them with our long and arduous method, and then we get to some prime number n minus 1, and then finally our last prime number, right? There's only finitely many of them. We can list them. This is the part that always throws me off. We can list them all. So now let's do something crazy. We've got our whole list of primes. Let's multiply them all together and add 1. So let's suppose a number n, capital N, is equal to the sum, what's the word? The product of all of them plus 1. So P1 times P2 times so on and so forth times Pn plus 1. And so since we've added 1 here, since we added 1, then we can say that n is greater than the big product. So n can't be a prime number. So n is greater than P1 times P2 times da 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 times Pn. And capital N is not prime because we've listed them all and we multiplied them all together. So n's not prime. That means n is composite. And so if n is composite, then we can write it as some number b times q. Which I might write instead as where we talked earlier about we can write every composite number as this product of primes. And so that means that there's so there exists some prime. I don't know where it is in the sequence of primes. So I'll call it PI, where we have numbers 1 up to lowercase n. And so I is greater than or equal to 1, and also greater than or equal to lowercase n. So it's just somewhere in that sequence of primes. And so there's some prime that divides n. So that's all well and good. But let's look at that. Let's tease that one out for a second. So there's some number pi which divides n. However, we've multiplied all the primes together. And so n is equal to like q times pi, where if we have like 2 times 3 times 4, this is equal to 2 times 12, right? Where we can like pull that number out of a product. And so if we pull pi out of this product of primes, it's that plus 1. And so what this means is that if we compute the modulus, so n modulo pi is going to be what? Well, so from here we know that it would be, from here we say n mod pi has to be 0. But from here, we add 1. And so therefore, n mod pi has to be 1. This is our contradiction, where we have, so if n is composite, then we can write this. But since we constructed our number in a way where we multiply all the primes together and then add 1, this is where our contradiction comes in, where we say that n mod pi is equal to 1. And this is a contradiction. And so for that reason, we've reached our contradiction. So that means our hypothesis must have been false. So there are infinitely many primes. Questions, concerns? So we start off by proving and like supposing our contradiction, and then we can list all of them. Let's multiply them all together, add 1 because we can, and then we explore the implications of that, where n's got to be composite because it's not part of our list of all the primes. And so if it's composite, then there's some prime that divides it. But because we added 1 to that big, huge product, there cannot be a prime that divides it. So because of that, then we get to the point where like, okay, so we didn't list all the primes. Like, because if there's no prime that divides n, then n has to be prime itself. And so because of that, we didn't list all the prime numbers. Therefore, we failed. And there has to be at least 1 more prime. And so the idea that we listed all of them is false. All right. Sorry, I was hoping one of the comments on the exam was like more problems in class. I'm trying to. Next time we'll talk about the Euclidean algorithm, and I'll try to have 1 or more of the homework problems for us to work on and warm up with. Thank you. I will see you on Wednesday. Let me know if you have questions on your exam. Did I grade homework 3? No. I will give it to you on Wednesday, I promise. And I'll also have homework 4 graded. Homework 4 is going to be easy to grade. Yeah, I apologize.
Okay.